This is section 3.11, part C, and we're going to continue to look at models that use the number E. This time we're going to look at sort of generalized growth and decay models. Our function, our exponential function now, will be a of t equals a naught, the initial amount, times e to the kt. This is now a continuous growth function rather than an annualized one, because we're using that continuous growth base, e. The number k is called the continuous exponential growth rate, or sometimes just the exponential growth rate. So we're going to look at first a problem that we've actually seen before, just for comparison purposes. Here's that nuclear disaster at Chernobyl again. Cesium-137 has been released with a half-life of 30 years. And I'd like to work by hand to find an exponential model of our continuous form for the amount of cesium-137 T years after 1986. So once again, at time 0, which is 1986, we would assume we start with 100% of the cesium that was released. And then since the half-life is 30 years, after 30 years we'd be down to 50%. Instead of A, I actually have P, so I'm going to write P equals P naught, e to the kt. And as often happens, we know the original y-intercept, or the P naught, is 100. We'll follow a similar process to what we did before. I'm going to take my second point, and I'm going to substitute that in. P is 50, and T is 30, so I'll make that 30K. To solve for K, I'll start by dividing by 100. So we have 0.5 equals e to the 30K. Got to get rid of that exponential base e, so I'll use the inverse function, the logarithm base e, or natural logarithm. The natural log and the exponential base e are inverses, so we can get rid of those. And that's just 30K. So dividing both sides by 30 is going to give me the value of K. And I have about negative 0.023. That negative growth rate, about negative 2.3%, is reasonable since the amount of cesium is decreasing. So my model is P equals 100 e to the negative 0.023 T. Again, our value of K, negative 0.023, is our continuous exponential growth rate, or in this case it's really a decay rate, and that says that the cesium-137 decreases at the continuous rate of 2.3% per year. If I compare that to what I got when I used the other method, I'll notice that I really got the same thing. I'd have to go out more decimal places to see a slight difference in that value. All right, how long will it take for the amount left in the environment to be 10% of what was released? So the percent is 10. And once again, I want to solve for t, so in this case I have to divide by 100. which gives me 0.1, equals e to the negative 0.023t. I need to get rid of my exponential base e, so I'll use a natural log again. Allowing my inverse functions to work. And then if I divide by negative 0.023, I get a little over 100 years. Again, I'm going to remind you that last time we did this problem, we actually got just a little under 100 years. The difference here is really just the amount of round-off error that we had when we did this. All right, finally, comparing our results, we've already kind of done this. We get similar results. Using the two models. All right, one more example for our growth and decay here. We'll have a growth one this time. We have the population of a certain city was 10,000 in the year 1980, and it's been doubling every 10 years. I'd like to find an exponential model of our new form, our continuous growth form, for the population of the city t years after 1980. And actually, I'm going to do two things. I'd also like to find a form population equals a b to the t. Let's do both. It'll help us actually to answer the second question. So, first of all, a equals a naught e to the kt. We know for sure that we started out in 1980 with 10,000 people. So a naught is 10,000. And then we were also told that the population doubles every 10 years. So doubling would be 20,000 people. When t is 10. So that will make that 10k. If we divide both sides by 10,000, we'll get 2 equals e to the 10k. And then I'll apply that natural log to both sides. The natural log of 2 is equal to 10k. And if I divide both sides by 10, I get a k value of approximately 0.0693. So my function is going to look like a equals the starting population of 10,000 times e to the 0.0693 t. All right, let's redo the exact same problem, only this time I'm going to use the model p equals a b to the t, our annualized growth problem rather than a continuous growth problem. I do know that my y-intercept or starting value is 10,000 again, and I'll essentially approach it the same way. Population doubles, so 20,000. Equals 10,000, b to the 10th power, took 10 years to double. Dividing by the 10,000, 2 equals b to the 10th. And I'll raise both sides to the 1/10th power. to get a value for B. And that's about 1.072. So I have P equals 10,000 times 1.072 to the T. Sorry, I should have given us a little more space there. All right. So they ask, what is the exponential growth rate for the population? And then what is the annualized growth rate? The K value here is my exponential growth rate. Or about 6.93%. To find the annualized growth rate, we have to interpret the B value here, change that to a percent, 107.2%, subtract the 100% that we started with, and our annualized growth rate is 7.2%. This compares directly to what we saw with that annual percentage yield versus the continuous percentage. Notice that the actual annual yield percentage is a little bit higher than the continuous rate. All right, the final question, when will a population reach 100,000? Let's go ahead and use our continuous growth formula for that one. I'm going to go back to this one here, this 10,000 e to the 0.0693t. And we want to reach 100,000 for population, so 100,000 equals 10,000 e to the 0.0693t. To solve our equation, we'll divide both sides by 10,000. So 10 equals e to the 0.0693t. And then we'll take the natural log on both sides. Allowing the inverses to work. And then finally dividing by the 0.0693. And it looks like a little over 33 years, 33.22. 33.23. So let's see, since we started in 1980, if we add the 33 years, that would be during the year 2013, partway through. All right, that brings us to the end of section 3.11.